Hey, hello guys. So in this video, we are going to discuss about union find algorithm. The union find algorithm basically used for cycle detection. It is also used in minimum spanning tree detection by Kruskal algorithm, and there are various other applications where we use union find algorithm. So we will discuss about union find algorithm, what is that union find algorithm and how we used it and which kind of problem basically it tries to solve by union find algorithm. So let's take an example. Suppose we have some company names and their subsidiaries names. So suppose we have some examples here. In the left side we have subsidiaries and in the right side we have company names, or we can say these are the parent company names for those subsidiaries. Just like as in Picasa, we have Google as a parent company, Google Fiber has a parent company named Alphabet, YouTube has parent company named Google. So there are an overall five companies listed in this mapping, and two of them are parent companies. Which one we can basically use to represent those subsidiaries as well, or in either way we can use them. So those two unique parent companies we have in this mapping. There is no any conflict in this mapping, and we can directly say we have those two parent companies, and overall we have five companies, and out of them three are subsidiaries and two are parent companies. Suppose we added one more mapping in this list. Suppose we have that one more mapping which is saying Google is a subsidiary of Alphabet. Now here we can see that Google was parent for two other companies in the same map, for YouTube and Picasa. So what we have to do in that particular case? In that particular case, we cannot say Google is a parent company because Google is also a subsidiary of some other company. So what we have to do? We have to just trim those Google and put the ultimate parent name in this list. So what will happen once we will do that? Alphabet will be the only parent company, as we can see in the right side. There is only Alphabet. There is only one company name, which is ultimate parent for all those five companies. Okay, so that is the basic problem which we solve by union find algorithm. So union find algorithm has two terms. One is union and another is find. Union basically just something we have to merge two things together. Like in our example, uh, we used Google and Alphabet mapping in our existing map. So we have to basically merge that particular mapping in our previous map. In the previous map, we had three mappings because our was a subsidiary of Google and YouTube was a subsidiary of Google and Google Fiber was a subsidiary of Alphabet. But once we take a union with some other term which say was saying Google was a subsidiary of Alphabet, we have to remove those Google from parents and we have to append Alphabet instead that. So that is the whole operation we does in union. We are supporting a new element. We are just supporting a new element in our existing map, and we are reflecting it its impact on all other existing mappings as well. So that is the basic what the union will do. And what are the find in union find? Find is simple, nothing other than that. In union, we have to find is there any parent which is a subsidiary in our new existing mapping. We are finding that particular value, like in our case Google was a subsidiary and in our new mapping and it was parent. We are finding that particular thing in our existing map. That implementation of find will do in that. Okay. So we will do those implementation, and these are the applications of union find algorithm. Partition of a set, we will discuss it in further series of we will discuss in further videos of this series. And track connected components, cycle detection, this one we will solve in this video. Kruskal algorithm to find minimum spanning tree, that one we will cover in another video of this series. Okay, so when we will code for union find, we required some graphs. So that particular graph, sample graph, we will use for our coding part, and we are not going to implement it. Uh, if you wanted to know how to write a graph and some more details on graph, we can create some other videos on that. Okay, so here we have some graph implementation, and those are the ages and their weights, which is basically an undirected graph. So this kind of graph we will plot. Okay, so that same graph we will use in our all union find algorithms. It either be minimum spanning tree computation or either cycle detection. So we will use that particular graph. So guys, let's move on the implementation. We will import test graph and implement our union find algorithm there. And for that, we will design it something like that. We will implement find, then union. Then since we are going to solve cycle detection problem, so we will have two functions for that. One will, is there any cycle, or another we will find cycle in a graph. So we have find, and we will define its body once we will finalize all these steps. Okay. Union. Now we will check is in cycle. We will provide u and v. U and v will be the values of two nodes. So we are basically checking if that age, if we will add in our existing groups, it will make a cycle or not. Okay, so that implementation we will do in is in cycle. Now we will iterate through all graphs. So we will have a function uh, is graph cyclic. Okay, so in this function, we will call test graph. From test graph, we will check number of vertices, and we can check those vertices from undirected graph. There are number of vertices defined in self vertices, and edges are in self dot edges. So we will use those values in our union find. So we will iterate through each vertices, and for each vertex we will check what are the adjacent connect, or basically what are the connected edges with that vertex. So we will fetch up, we will iterate through all those vertices. Yes. So from edges we will fetch those connected vertices. Okay, and then we will check is that edge present in cycle or not. If it is present, then we will say yes, we have cycle in this graph, and we will print that and break this loop. Otherwise, we will union that particular age in our existing parents. Okay, so I think we should return at that time, because once we found that there is any cycle, we didn't go further. ahead in this graph. We can just simply return we have cycle. Otherwise, we will say graph is cycle free because we check each edges and all are belongs to a different parent, belongs to different subgroups. So we are cycle free in that particular case. Now we will implement our find union and is in cycle functions. For that, I think we should implement parents as well, where we will maintain all the ages. Those are present to which group. So we will initially we will have it -1 for each vertices. So test graph dot vertices, everything will have -1 value. We will provide those parents to each is in cycle function as well as union function. Okay, now is in cycle. We have parents u and v. So for those u and v, we will call find and fetch out the ultimate parents of their u and v. So we are basically for a subgroup, we are trying to find out the ultimate parent. So what we can say, we are suppose we have a group and we assign a name which we are calling parent. So we are fetching a subgroup name for each and every node. In that manner, we can understand it. So if if we found that those two nodes belong to a same group, that means both have same parent. That means those are in, if we will add that uv, it will form a cycle, so we will return true in that particular case. Otherwise we will return false. Okay, so now we will implement union. Union has parents u and v, so we will add those parameters. Okay, so for union, we again call ultimate parents of u and v, and we will assign new parent to x, which will be y. Okay, it's the same thing we did in our example, like in case of Google, once we added Google and alphabet mapping, we reassigned every Google value with alphabets in our existing maps. Same thing we did in union. So now in find we have parents and in node. So what we will do, we will check if parents of that particular node is equal to -1. That means that node doesn't have any other parent. That means it is the ultimate parent. So we will return you that particular case. You. Otherwise, we will recursively call find for the parents of u. So it will go until we didn't find -1. That means ultimate parent. Yeah. So that's enough. We can do in union find. So that complete code will be used to find cycle in a graph. Okay. Okay, so guys, in this implementation which we did for union and find algorithm, we can see we were recursively calling find function for each and every node. So finally, it will increase our time when we will call each and for each and every node a same recursively, and we when we check the whole path, we will find out that there are a lots of duplicate iteration we will make. Suppose we are going from a leaf node to the root node, and there are some intermediate nodes are present in this path. We will recursively call for those intermediate paths again and again. So what we can do, once we iterate through a path, we will store those values and we can use directly those values. In that manner, we can optimize our find function. And there will be some issues with our union function also, because what we were doing, we were just adding those values one by one without making any optimization in it. So that that can make a chain which we can understand, which may be similar to some linked list. We will go one by one when we have to iterate through it. So suppose we have four items. Suppose we have four items: 0, 1, 2, and 3. So initially those four items will be a separate node, and then we will start our union here. We will initially do union between 0 and 1, and it will be something like that. We are assuming 0 as a parent and 1 as a leaf. Okay, now we will do union between 1 and 2. Again, we are adding those values in this chain. 2 will be a child of 1. Okay, so again we will do union between 2 and 3. Now when we will add this to our chain, okay, so what kind of a structure it looks like? It like a chain. When we have to find out the parent of 3, we have to go through each and every items, and then ultimately we will find out that 3 has a parent as 0. Okay, for 2 we will do same operation, for 1 we will do same operation. So what we are doing here, we are not optimizing out when we were making union. When we will go through this chain, we have to go each and every steps. So instead that we can do optimization in our union, what we called union by rank. So we will append some rank values with each union, and on the basis of that we will do our union operation. So what is union by rank? By union by rank, basically we'll check minimum depth of nodes, or we can say tree. Suppose in our initial case we were making union between 0 and 1. We will do this. Now we have to make a union between 0 and 1 and 2. So now we will check the depth of 1 and its ultimate parent, which is 0, and what are the depth of 1, it will be 1, and what are the depth of 0, it will be 0. So we will add our new value 2, which will be associated with minimum depth as per our definition. So that 2 will be attached with 0. Okay, so now we have to make a union between 2 and 3. What are the depth of 2, which is 1? What is the depth of ultimate parent of 2, which is 0? So we will add it with 0. So from that new structure, we can say we are doing lots of enhancement. While we were making union, we can see it. So what will be the enhancement there? We are going from order n to order of log n. That big improvement we will make between union operations. Yeah. Okay, so let's implement what we discussed. So we will call test graph test graph, and we will define our find function as we discussed. It will have parents and u. We will implement it. We will implement union. Then we will implement our is in cycle function. Cycle function that will also have parents u and v. I always get that typo error. Now is graph cyclic. Okay, we will make an object of this test graph. Again, we will iterate through those vertices and edges, connected nodes from those edges. Okay, so again we will check is in cycle and v and print a message. Yes, cycle found. And return. Otherwise, make a union. And at the end, we will print graph is cycle. Okay, so here is some parents. We have to implement it. Parents. Okay, so as we discussed in our union, we will maintain some rank with each parent, and on the basis of those rank, we will add our values where we have to add this. To make that ranking mechanism, we have to instead just putting some integer values in integers to denote that parent, we need two values for now. One will denote our parent and another will denote our rank. So we will create a class for that. Subset. We will define constructor of it. It will have parent and rank. And object level parent will be parent and object level rank will be rank. Okay. So for each vertices we call those objects. Okay. We will expand each objects of subset with no parent u. We are assigning self parent initially and rank 0 for each and every nodes. Okay. So now let's implement define same as we did in our basic implementation. Find will check if parents u dot parent equal to u. That means we have u as a parent, or we can say it is a self parent or ultimate parent. Ultimate parent of the group. Otherwise, we will do same operation as we did in our basic implementation, but what we will do here, we will memorize what we will get in return. So we will store it in our, we will update basically our parent. Parents u dot parent dot parent. That value will not be, that will be parents. We are returning a node and we will return parents. Okay. So here we can see we have two return function and both are the same values. So what we can do, we can restructure that code by making that condition with a negation, and we will call parent if we will go inside that. Otherwise we will return parents only. Okay, now okay, so let's start our union implementation. Uh, so we will call our find as we did in our basic implementation. So we have ultimate parent of u and v in x and y. Here we will not just simply check x and y, we will check what is the rank of it, and on the basis of that we will assign value to that parent. If x dot rank is greater than y dot rank, that means x has higher rank. So a higher rank basically we are assuming as a parent. So what we will do, y dot parent will become u, and if x dot rank is less than y, it will become u. Otherwise, that means we have same rank for both x and y. We can choose any one of them and increase its rank. That's all. Since we increase rank of x, so x will be parent. That means we will be parent. And yeah. So here we used our ranking mechanism. We are choosing which one is the better one. On the basis of our ranking, it will optimize our structure. Okay, so is in cycle we will call ultimate parent of u and v if x dot parent equal to y dot parent, means both belongs to the same group. Return true, yes, it has cycle, otherwise return false. Yeah, so that's our final advanced implementation of union and final. In this implementation, now we will find out what are the various complexities we are encountered. First of all, let's check that subset function. It will take order one because we are not doing anything in it. We are just assigning those values. Then that find it will have a inverse accrement function of n. That inverse accrement function we can discuss later. Meanwhile, we can understand it will be something just equal to log n. And those two parent function also have a command n. We are calling same parent function. Rest of other than will have order one because we are not doing anything else. So yeah, that's all complexities we will have in this implement. Yeah, so that's all for this union and find algorithm for cycle detection. We will meet you in further series of union find algorithm where we will do implementation of partition of a graph and minimum spanning tree via cross cut. Okay, hope you enjoyed today's video. Thank you. Bye.